Do you ever notice sometimes driving on the highway when some people just brake for no apparent reason every 2 minutes? Like, just because there's a slight bend on the highway or something like that. That gets on my nerves so much. And not just because I have to watch out for people slowing down in front of me, but because of the energy wasted. Let's do a little comparison. Let's think about how much energy it takes to accelerate from 0 to 40, and therefore how much energy is lost when you brake going from 40 to 0. And let's compare that with the amount of energy that it takes to go from 70 to 80, and is therefore lost to heat when you brake from 80 to 70. And we don't need exact numbers here, we just need a ratio. We need to figure out the proportionality. And because we're just comparing two values, it doesn't really matter what units we use. So let's have some fun here. We're going to make up a unit in a minute, but let's look at our equation first. The change in energy looks like this. The change in anything is its final value minus its initial value. And let's throw in our actual equation for kinetic energy. And now let's simplify that a little. So we can see that the change in energy, or whatever energy is wasted when we brake, or whatever energy we use to speed up a certain increment of velocity, is proportional to the square of the final velocity minus the initial velocity. So if we're going from 0 to 40, or think about braking, you come to a stoplight, you're going 40 and you brake to 0. This is also how much energy is wasted through friction when your brake pads scrape against your rotors. And then if we go between 80 and 70 miles an hour, we can put in those numbers. And I don't know what the car weighs, I don't know its mass. So here's where we can make up our own unit. Since we can kind of do this since we're just comparing one value of Ke to another. Let's make up a unit called the car mass. So a car weighs 1 car masses, just because I said so. So let's say the mass is 1. I mean, really, that's all there is to a unit. We could define it and say, like, 1 car mass is 950 kilograms or something like that. And that would be our conversion factor to convert from car mass to kilograms. So our car is always going to weigh 1 car mass. So that just simplifies things for us. What's 40 squared? Should be 1600 about. And 80 squared should be about 6400. 70 squared is 4900. And the difference between those is 1500. And now we can compare these two values. So what we're really looking at is the ratio of the energy we waste braking going from 40 to 0 and the energy we waste braking going from 80 to 70. And we can see here, here's what I wanted to show, is that they're almost equal values. Maybe the energy going from 40 to 0 when you brake is about 5% more than going from 80 to 70. But essentially the same, close enough for me. So this is saying to me that probably you're wearing your brakes just as much when you like suddenly decrease from 80 to 70 on the highway as you do when you come from 40 to 0 at a traffic stop. And it just happens so fast on the highway. So I'm not an expert in cars, I'm just hypothesizing here, but maybe because it happens so fast, the heat builds up more and actually wears your brakes more. But what this also shows here is that speeding back up from 70 to 80 on the highway uses just as much gas as it takes to go from 0 to 40. And here's something to understand. I should have probably explained this more earlier. But when you do brake, the kinetic energy is getting converted to heat energy. So it stops being mechanical energy because it's not kinetic energy anymore because your car slowed down. It's not potential energy because your car didn't raise its height. So there's no gravitational potential energy gained. There's no elastic potential energy gained. So that energy is pretty much just gone, and it's used to it basically gets wasted by heating up, the temperature of your brakes and rotors, and that's called thermal energy. So you're basically converting the kinetic energy to thermal energy when you brake. And if you don't believe my analysis here, think about it in terms of work. You're applying, when you're going from 40 to 0 and you brake, the force of friction is applying a force, that friction between your brakes and rotors, and you're slowing down over a shorter distance because you're not going as fast when you slow down from 40 to 0. But if you're going 80 and you slow down over the same amount of time, you're applying the same force, and you're going a much greater distance because you're flying along at 80 miles an hour. So if you do that same braking, the distance over which you apply the force is going to be greater, much greater per every 10 miles an hour that you decelerate. The total distance that you take to decelerate from 80 to 70 will be about the same as the total distance it takes to decelerate from 40 to 0, and hence the work done by your brakes is about the same in either case.